Welcome, everyone. Cosmos DB Live TV. Thanks for joining us this week, episode 13. And this week I've got with us a very special guest and someone I really admire, Matias Quaranta. Matias works on our .NET SDK team, and he is responsible for some of the most loved features, I think, maybe in our SDK. I think you wired up the change feed. You don't do the back end for the change feed, but you do all the front end, all the SDK piece for the change feed. I think bulk mode, I think, is you, if I'm not mistaken. Transactional batch is you, if I'm not mistaken. I can't tell you how much I love transactional batch, because you know why? I really hate writing stored procs in JavaScript. And you really, now that I can do them in the SDK, I basically show that to anybody and everyone whenever I'm doing demos. I'm like, check out this feature, transactional batch. You will love it. So anyway, welcome. Good to see you.
Thank you, Mark. Thank you, everyone, for having me. For me, it's a super pleasure to be here. I got the lucky number for the episode. I was lucky enough to work on the SDK, and we are a team, so every single feature is, like you said, it involves backend, it involves frontend, it involves SDKs, it involves different libraries. So it's kind of like a team effort to ship those features, and it's super great when we see users actually using them to be successful and build applications. So yeah. It's always a pleasure, and that's basically the idea with this talk today. I mean,
so today you're going to show us some of the coolest kind of tips and tricks, internals, advanced topics. Basically, I guess if you're a user of our .NET SDK and you're trying to eke out every single kind of ounce of performance out of this thing, this is probably a good podcast for you to join. Would that be right?
Yeah. We'll try to kind of pop up the hood. I think that's the expression. To know what's happening inside the SDK in terms of connectivity, what happens on each operation, which are the best practices. The idea here is if you are writing an application from scratch, or maybe you already have an application in production, just check which are the things that you should be doing to avoid the most common pitfalls, and then we'll cover the most known scenarios for cross-regional failovers, because as we say from Cosmos DB, we want to provide the highest possible availability, and the SDK plays a kind of like a really big part in that. So we'll go through different scenarios, the most common ones, and how the SDK behaves, and which are the expectations that you should have in cases where your SDK is configured correctly.
This is great. We have not yet talked about availability and failover on this show. So this is great that you're going to talk about it today. So fantastic. So where do we start off with your talk here? Connectivity modes, it looks like.
Exactly. So before talking about how the connections are maintained and how the payload travels and everything, I wanted to start with the basic. Which are the connectivity modes that you have available in the SDK? If you are building an application, which are the options that you have when you are using the SDK to connect to your account? But actually, before going to that, I wanted to take a couple of steps back and do an overview of the system topology. We know that we can create containers or collections, and when we create containers and collections, these containers might span multiple physical partitions. As your data needs grow and you keep storing more information, these physical partitions will keep increasing to accommodate your data needs. Now, each physical partition is actually composed of what we call 4 different replicas. And these are 4 different machines in 4 different racks in a data center. So the failure percentage or the possibility that all these 4 machines fail is rather small, because they are separated in different Azure racks. And if you are adding multiple regions to your Cosmos DB account, then this partition is actually replicated across each region. So you have 4 replicas in each region. Whenever you save a document on the Cosmos DB service, what happens is we take the logical partition key that you are sending with that document. We apply a hash algorithm, and that tells the system which physical partition that document should be stored in. When that document is stored in one of the replicas, then that's also replicated in all the 4 replicas within the same partition. So your document is actually copied or replicated 4 times within that same region. And then if you add more regions, then that document is also replicated across all the replicas in all the other regions. So that's kind of how we are achieving a high availability of the data, because it's actually being replicated all over. And the chance of actually all these components, all these machines across all these regions failing at the same time, it's rather small. So now that we know that a physical partition is backed by 4 replicas, that kind of will help us understand how the 2 different connectivity modes work. Now, kind of in front of these replicas and partitions, there is a component we call the gateway. If some of you might have read the REST API documentation for the service, you know that you can interact with the service through the SDKs, but you could also write your own REST wrapper, REST API wrapper, and send HTTP requests to the service. And the component that takes care of receiving these REST API calls is something we call the gateway. The gateway is a set of machines that is in each region and handles all the HTTP requests that hit the service and provides information for example, getting the account information like the consistency, the topology, which are the different partitions that we have available, the information about the collection, information about routing that we'll see in a little while. But it kind of gives you all the what we call the metadata about the account. And it lets you do operations that we define as management plane, which is creating a database or creating a collection. And then it also enables you to do data plane operations like creating a document when you interact through the REST API endpoint. Now, that kind of gives me the kickoff of which is the first connectivity mode that you have available when you use the SDKs, and which is the gateway. And by the name itself, what it says is the SDK will use the HTTP protocol to connect to the REST API, and then obviously the gateway to issue all operations, all management plane operations when you create a collection or you create a database, and also when you do data plane operations, you create, read, or execute queries. Everything goes through the HTTP protocol, through gateway, and then gateway, what it does is it opens these TCP connections to the backend replicas to actually execute the operations. It gets the results from the backend replicas, and then basically pipes or returns the result to you or your application as the caller. The other connectivity mode that we have available is the one that we call the direct mode, which is basically your application, instead of going through the gateway, it connects directly to the backend replicas through TCP. So it opens the TCP connections to the backend replicas and the backend partitions, and then executes the operations directly there. So which are the big difference between these 2 modes? Well, the first one is obviously the protocol. Gateway uses HTTP, while direct mode uses a TCP protocol. Gateway mode is more compatible with enterprise environments that has proxies or hard network rules where you can only open a particular subset of ports, maybe very limited, where you can't, you are limited in terms of which are the URLs that your application or the endpoints that your application can connect to. It obviously uses less ports and less connections because we are basically just opening up an HTTP connection to the account endpoint, which is normally your account name .documents.azure.com, and using the port 443 for HTTPS connectivity, and then sending the operations through there. Obviously, if we kind of remember the diagram we just saw, the gateway mode has more or has a higher latency than the direct mode. And the reason is you have the network hop in the middle. You're not directly reaching the backend replica, but you are just connecting to gateway. Gateway is relying your operation to the backend replica, getting the result, and then returning the result to you. So you have that extra latency there, which is obviously what the actual benefit of the direct mode. The latency on the direct mode is actually backed up by our SLAs. So the operation latency that you have once your request reaches the replica, it's always I think if I remember correctly, it's like 10 milliseconds for read and write operations. And that's super fast compared to Gateway. Not saying that Gateway is going to be super slow, but rather that if you compare the latency between the two modes, direct mode will always be faster. And that's one thing you need to keep in mind when you are making the choice. I mean, we always recommend direct mode, but direct mode, while it has the pro of being faster, it also might have the issue of using a higher number of connections and a wider array of ports that you need to open when you are connecting to or using the connectivity mode.
So the thing I often hear with customers who have issues with direct mode is SNAT exhaustion.
Right, exactly.
Kind of the thing in there. And they can get around that if they use like a private or like a VNet or subnet using service endpoints, I think. Is that correct?
Yes, that's correct. I mean, there are a couple of workarounds. Normally, and I don't want to go over it right now because it's something I will comment in a bit. But yeah, it's one of those scenarios where you need to keep in mind that this will use more connections than gateway mode. This will use more ports. So if your application runs inside like an enterprise environment, you might need to open more ports in those network configurations. So those are things that you need to compare and see which of these two modes is the right for me in this particular setup and environment.
Got it. So what I guess the difference then too is, I mean, even if direct mode, you still have to connect to the gateway first of all and download or grab all the mapping information, correct? And then it just basically treats your client like a gateway, doing all the physical partition, the PK range mapping, rather than having to do it from the server, right?
Exactly, and that is actually that was a good point, because that's actually the next point where I'm going to discuss. So normally the first question is what? Okay, so I have the two connectivity modes. I create my client and I do my first operation. So what happens when I do, like, for example, create item? I create a client, I call create item. What happens then? So what we do is the SDK will, on that first request, it will call to the gateway using HTTP protocol and obtain some information that we need to in order to execute that particular operation. And that information is the account information, for example, which regions is the account replicated to, which is the consistency for this particular account. We also fetch the container information. You're executing this operation in some container or some collection. So we need to understand which is the partition key definition or partition key path for this container. And finally, like you mentioned, we need the routing information, which tells the SDK which are the addresses for the different partitions that this particular container is using. Once we have that information, what we do in the SDK is we store it in a memory cache, and then we open the TCP connection to the backend replicas and execute the operation. When a second operation comes afterwards, the first, then we have all the information that we require on the cache, and we will just reuse the TCP connection, which is already open, and send that operation to the partition. Now, in the case where maybe this second operation is to target a different physical partition, the only difference is we will open a second TCP connection and execute this operation on a replica of the other partition. Now, obviously, this example has only two partitions, but this is when you start to see why the direct mode might have more connections than the gateway mode. Because as your partitions keep getting bigger, or if your collection has many partitions, then these TCP connections need to be established to the different partitions as your operations keep happening, right? So this is kind of what happens underneath the hood whenever you start to perform operations. And I have a small, since we have plenty of time, I kind of feel a small code sample to showcase that and to show you. So this is B3 SDK. It's just calling create item with like a very random model. So what I'm going to do is I'm going to just run this, and on the other side I have Fiddler. So what I want to show you is which are the HTTP requests that happen on the first request or the first operation that I do on the SDK. and then that those requests don't happen after that first one, as I keep doing operations, right? So what I should see is once I start the application and I hit that endpoint here. Okay, this is okay. I got it. So this is my Fiddler. I'm gonna do some zooming here because Fiddler that doesn't let me, increase the font. So
Oh, bummer.
so once I execute that operation and I go to Fiddler, which should be here. Now I'm gonna do, okay, that's the breakpoint. So the first thing that we will see is this request. This request is actually the request to get the account information. You will see that that's my account name documents.azure.com, and it's actually kind of like an HTTP request to the root of that address, and that returns the if we open this guy and we go to what was the actual response, you will see that that is actually the information for my account, which are the regions. For example, this account is only in West US 2, right? And a bunch of other information particular to my account itself. And the SDK is storing this in an internal cache. Now, the same goes for the collection or the container. You see that in my case, the container is called episode 13. So we will have a request here with the account, with the collection information or the container information. And then we have the routing information, like you said, which are the partitions and which are the addresses. So once we have that information, then the SDK can resolve the operation. You won't see the actual operation here because we are on diary mode. So Fiddler is only tracking HTTP requests. So what I'm doing is I'm just starting a while loop, like an infinite loop, that obviously I have to move the breakpoint. But you will see that this guy is running because I'm seeing the logs here creating new items, but there wasn't any new HTTP request in Fiddler. And the reason is we already have the caches, we already have the connections open, so the next requests are just hitting the replicas directly. And that is basically the effect of how the SDK handles the initial connection and the initial operations.
Yeah, that's cool.
So going back here. Now, this is, I kind of explain that because it will help us be a baseline or some starting point to understand, okay, this is all great, but what happens when things don't go as planned? And which are the failure cases and failure scenarios that we normally see when troubleshooting issues on the SDK? And obviously, which are the things that you can do to mitigate or avoid those pitfalls? Before actually listing or going through all the different scenarios, one important thing is both the Java and .NET SDKs expose some critical information in the form of what we call diagnostics. So either for success scenarios where you are performing the operation and the operation completed successfully, or for failure scenarios. In this case, we have in .NET we have the item response or the response in of the operation, and we have a property called diagnostics. That diagnostics will have three important properties or data points. One is the elapsed time. So how long did that particular operation take between you calling or executing the operation and the SDK getting the response and then returning the response to you. Another piece of information which we'll see why it's important in a little bit is which are the contacted regions. Well, one particular operation might, in certain conditions, span multiple regions, and we'll see why in a little bit. But it's important to know that information is available for you on the diagnostics that are there either on the response or on exceptional scenarios. It's actually the same type, so it has the same API surface. It's diagnostics.getContactedRegions in .NET. And the other important part is actually the toString or the serialization of the diagnostics. What we'll see here, something like this. So it's actually a JSON that will describe exactly how much time it took on each step of the SDK, what was the duration of each network request, things like what's the CPU measurements on the actual machine for this particular, during the time this particular operation was executed on, and some other critical information. Like, for example, we measure the serialization of your payload, of your model, of your, in this case, your T or type that you're using, and we measure it, how long it took on the SDK to actually convert that object into a stream that can be sent on the wire. We also measure, like I said before, the CPU history, and we measure the network request that the SDK did. So here, in this case, in this example, we see this is the name of the TCP request that, in this case, it reached to one of the particular partitions. So here is even the address of that partition, which, if we kind of rewind a bit, we saw those exact responses on Fiddler. I mean, we saw which were these addresses. So this was the actual diagnostics of the SDK, opening the TCP connection, executing the request, and stamping the diagnostics with how long it took for that particular request to complete. And then we also have the, if there were any HTTP requests that were also part of the operation. So here we see the same things that we saw in Fiddler. We see the request for the addresses and the other ones. So it's basically kind of like the diagnostics is everything that happened in the SDK that could explain why this operation took the time it took, or why this operation failed in the way it failed. And this same thing, like it's on the .NET SDK, it's the same thing available in Java. So this is valid for both Java and .NET SDKs. And the amount of information is the same. I mean, the API names might vary a bit because it's in Java and .NET might have language differences in terms of how to access certain APIs, but the information is still the same. You still get the duration, you still get the regions contacted, and you still get the serialization of these diagnostics also in Java. Now that we know that this information is available, the biggest question is, okay, so I as a customer or as a user, should I store this information on every request? And the answer is, our recommendation is, you can, or it would be beneficial for you to store it in exception scenarios or in error scenarios where you get an exception and you are not sure what happened, so store the diagnostics. And for success cases, we've seen customers conditionally store these diagnostics for requests that they want to analyze. For example, they see a request taking more than X amount of time. You can check the duration from the diagnostics, or you might be having your own stopwatch or time measuring method that will tell you this operation took longer than whatever we were expecting it to take. So you can store the diagnostics, and we can use the diagnostics to analyze why that particular operation took longer. So it's a matter of making a decision on which is your threshold. Maybe that threshold is you are providing a service to someone else, and you have an SLA to to enforce on your own service, which also uses Cosmos DB. And for some reason, you have an operation that took longer than your SLA in your operation. So you might want to capture those diagnostics and understand what went wrong on that request to take longer. So those are things that you can do to capture those diagnostics. But that is information that we will use in the next couple of slides to start troubleshooting potential issues. Now, when we talk about errors or failures, it's easy if we split this in two groups. Like, which are the failures that can happen on the client environment, on the client machine, or on the client network, and which are the errors that might happen on the backend, and how to actually diagnose and troubleshoot those. The most common error is what we call the cold start, which, if we kind of refresh the diagram we showed earlier with the caches, which is the one that we are now seeing on screen, we know that the first request is always takes a bit longer. And the reason is the SDK needs to fetch this cache information or routing information, if you will, to obviously open that TCP connection and execute the request. Subsequent request won't take as long, but the first one might have a higher latency, and this is the reason. Now, how you can improve the latency and avoid this cold start? There are a couple of alternatives. Sometimes you can do like a phantom request, like trying to read a document that you know doesn't exist as part of your application initialization. That will populate the caches, but obviously will fail the operation. But you can be certain that all those caches are populated. The other alternative, and currently it's on something that is only possible in .NET, is, and I'm gonna just code it here, is if you have a, let's actually delete all this and reuse the information. So let's assume that you have your client with some configuration. We'll see which are these things in a bit, but let's say that you already have your configuration available. The Cosmos DB3 SDK has this API, which it comes very handily. Cosmos client dot create and initialize. So the create and initialize async API I have a helper to get the connection string, but this guy here, the point is it will not only create the client as if you were creating it from the normal constructor, but it will also fetch and populate all the caches required for a particular subset of collections that you want to interact with in this account. So
it's kind of like using the old open method on V2 SDK, isn't it?
Exactly. So V2 SDK has this open async method, but the problem with open async is if you have an account with, let's say, 50 or 100 collections, open async would prefetch all the information for all the collections. So regardless of what you are going to do in this particular application. So let's say you are creating an application that just uses one of the collections, right? If you call open async, that's going to take a long time.
Yeah.
It's going to open a bunch of connections or populate a bunch of caches that you probably won't use. So for V3, the approach was, don't do an open async, but have a similar API in which you actually create a list. I think it's, if the API is, it's a list of tuples. So it's kind of like list of string. Let's go with containers. And let's add this using up here. It's a list of tuples. And then you should do something like containers.add, and then here you put the live TV, which is my database name, and in this case it's EP13. So I add this container or all the containers that I want to use in my application, and I pass this guy to here.
Okay.
And this should be an await. So the idea is you can call this during the initialization phase of your application where you are constructing the Cosmos client. And this will give you back not only the Cosmos client instance that later you can use for the operations, but it will also pre-populate all the caches and do all those HTTP requests in order for your application to be ready once the first actual operation comes in. So you don't pay the cost of that cold start.
Makes sense. Yeah.
So those are two ways that you can actually work around the cold start, but just if you are not doing any of those, then know that the first request will have high latency, and the reason is, well, we need to fetch this account information and routing information, otherwise we cannot do anything on the SDK.
Is that parameter optional? What if I could I just call that with nothing in there and it'll initialize everything?
No, that parameter is not optional, and the reason for that is most of the use cases where we've seen customers complain about OpenAsync or use OpenAsync, they were never interacting with all the containers of the
Got it. Makes sense.
So, I mean, we could maybe, if customers give us their feedback on our GitHub repo that they would like to see this API, but with just Iterates everything. Like, give me all the containers. This is a use case for, or a business case for me, and I wouldn't like to keep having to enumerate everything. Then that's something that we can actually add. But it would be great for users to show that feedback in our GitHub repo.
Yeah, like you said, you could just make a fake call, just doing a point read or something, and then that'll basically do the same thing. So
yep. That's also valid.
Yeah.
Now, the other high latency scenario that is really common is, let's assume that you have a Cosmos DB account with 2 regions, right? And since you are building an application that is globally distributed, you mostly have your application also deployed in these 2 regions where you want to have local users access the information. So the concept here is you want each region to access or read the information as fast as possible from the closest Cosmos DB copy or replica. Now, what happens is normally if you just create the SDK, just passing your keys, what the SDK does is it by default connects to the primary region, which is, if you go to the Azure portal and you see the list of your account regions, it's kind of like the first one. So that's kind of like what we call the primary region. If you don't specify anything on the SDK other than your keys or your connection string, then the SDK will always connect to the primary replica. And if you are deploying your application to these 2 regions, let's assume that it's the same code that you are just deploying to region 1 and region 2, passing the connection string, then both region 1 and region 2 will by default connect to the primary region, which is fine in terms of latency for an application running in region 1, which is the primary region, but it's not so great for an application running in region 2. Because it's going to see a higher latency due to the, obviously, cross-region network calls. So how do you solve this? Before that is, how do you troubleshoot that? And normally what we have in the SDK, which is something I shared before, is in the diagnostics, you will have all the network requests stamped with the latency. And you will see which is the region that it is contacting, both on the actual diagnostics JSON and also on the diagnostic property that listed the contacted regions. So you can use that information to understand, okay, this application that was running in region 2, it is actually hitting region 1 when trying to execute this request. Something is not right with the configuration because I wanted this request to be hitting region 2. Now, how do you fix it is both also the Java and .NET SDKs, they have APIs that will let you hint or configure the client to tell which is your regional preference. Now, the .NET SDK has 2 options. One is called the application region, and the other is called the application preferred regions. And the biggest difference is the application region is meant for you to tell the SDK which is the region this application is actually running on. So let's assume that I have an application running in West US. I will set the application region on West US and pass that as configuration on the SDK. And what the SDK will do is it will use that region and it will create a map of all the regions that are geographically closer to West US 2 in this case, and then try to connect to those regions in your Cosmos DB account. So if your Cosmos DB account has, for example, West US and East US or Central US, and you pass application region West US, then this client will preferably connect to West US to perform the operations. Now, if you didn't have a Cosmos DB endpoint in West US, then it will use the closest one that is available in your account. But using kind of like the distance or the geographical distance in between regions. The other option is defining your own custom preference in terms of regions. This first option, it's basically, we will populate the preference based on distance. But maybe you have some business scenario where you want to have some preferred order due to some business logic that it doesn't correspond to regional or geographical distance. So the application preferred regions will let you pass a list of regions that you want to hint the SDK that it should use whenever it needs to perform operations. And the order is basically saying, if West US is available, let's use West US. But if it's not available, then I'd rather use Central US. And this is also available in Java, with the difference that Java doesn't have the first the first application region, it only has the list. So you just need to specify a list of one or more regions that you want to preferably connect to. And this will tell the SDK which region should it use to execute the operations, and not just let it to result to the primary region. Now, the other most common case of high latency is retries. Let's assume that I'm performing an operation. I'm calling the SDK and saying, create item. So the SDK will perform that request on the Cosmos DB service. Now, sometimes there might be some error cases or error codes that the service might return to the SDK. For example, the known 429, which means you are going over the provision RU or the provision throughput. So when the service returns these error codes, and we'll see a small list later on, but basically when we return this error code to the SDK will retry internally, and it will keep retrying until it succeeds. And when it succeeds, when the service says, okay, this operation succeeded, you have an okay, we'll return the result to the caller. From the application perspective, in this scenario, it might seem that the request itself took longer. If we measure the amount of time that it took this whole operation to resume, to success or complete, it took longer than if we didn't have any retries. But how do we spot these retries? Or how do we spot these internal retries that the SDK is doing in order to complete this operation with the higher latency? And we again go to the diagnostics. If we open the diagnostics for this particular example or this operation, we'll see something like this. We'll see multiple network interactions, each with maybe a potential different URL or time, but we'll see the status code of the responses. So in this case, we'll see that the SDK did perform one request, but the response code was too many requests, which is 429. So then we'll see the other request on the SDK that eventually had an okay. So with these diagnostics, we can obviously say, oh, okay, this particular request took longer or had a higher latency because I had retries. Now, what should I do when I have these retries? Well, it kind of depends on the nature of the retries. We'll see some example later on. In the case of a 429, it might just mean either increase the throughput that you have provisioned because you are exceeding the throughput. You also have the option of using autoscale if your workload is spiky and it's not constant. You might want to use autoscale to define some boundaries. So when you do have this spike in traffic, you are not hitting these 429s because autoscale is increasing their use for you in order to absorb the spike, and then it will go down as your usage decreases. The other option is obviously reduce the workload or perform less operations in order to maintain your workload in the margin that your provision RU or provision throughput lets you perform. But the whole point is the diagnostics will let you have this insight, and this will explain why that particular request took longer. And the other most common error scenario that we see are timeouts. As we've seen in the previous slides, we can have HTTP request and we can have TCP request. But this is just we all know this is just a machine in a box, and there are wires that go somewhere, and these wires go through other infrastructure and eventually hit or reach the Cosmos DB endpoint, right? And there is always things that can go wrong in terms of infrastructure. So one thing that if you had to take away from this talk, it would be ideal is when we are building applications that should be resilient or fail tolerant, we always need to keep in mind that these timeouts can happen. And having one timeout in an hour is something that might happen. Depending on the whole network infrastructure. It could be a failure on the machine that I'm actually executing the operation. It could be a failure on the wire. It could be a failure on a router somewhere in the middle. There's always a possibility of a failure. So when I'm building these applications, I should take timeouts or connectivity timeouts into consideration when I'm building my business logic. Now, it is expected that maybe one or two or very few timeouts happen within an hour or some period of time. Yes. What we don't expect is to have a really high amount of timeouts. When we are seeing like 10%, 5%, 50%, or in the worst case scenarios, 100% of my requests failing due to timeouts, then that's when you kind of want to dig in and see what's up. I mean, this isn't expected. Now, these timeouts that are exceeding the common or expected threshold tend to have two most common sources. The first one is CPU, and you might wonder why high CPU might be a source of timeout. Well, CPU is a resource, right? And you're executing code, and that code is actually wanting to put some bytes or some payload into the wire. Now, if your CPU is overloaded, that operation of putting that payload into the wire might take longer than what we expect. And when that happens, well, you have a timeout because we couldn't just process that request in the expected amount of time. Now, how do you diagnose a high CPU timeout? There are a couple of tools there. One is obviously, again, going to the diagnostics. What we do in the SDK is we snapshot the CPU usage every 10 seconds. And we stamp that information in the diagnostics of the operations. So you will see something called the CPU history, and it might have a couple of lines like this. So every 10 seconds, we stamp the CPU. Now, if you see, like in this example, all these stampings showing 100% CPU, 70% CPU, or something along those lines, then this timeout is potentially due to CPU being high. Now, why CPU could be high? Well, it might be some bug in the application, some code that is actually rising the CPU usage above the expected level. It could be the application, processing a higher workload that you normally have. So higher workloads, higher amount of operations, more resource consumption, the CPU is getting hammered. That is one potential scenario. The other scenario that happens mostly on .NET is something we call thread starvation. And we normally diagnose it also by looking at the diagnostics. But when we see the CPU history or these stamps not happening every 10 seconds, this is something that might be hitting at thread starvation. And the reason is the component that is measuring CPU is totally independent from the SDK itself. So that there shouldn't be anything on the SDK blocking that component from taking measurements. But if your application is experiencing some deadlocks, then that could cause thread starvation, and that could cause this component to take measurements in times when it's not expected. So maybe your CPU is not high, but if your measurements are not every 10 seconds, something is up on your thread pool. Normally, what we advise is, in these cases, there might be some code on the application executing async operations by blocking threads, or commonly in the .NET world is execute sync over async, which is take the async operation like I had in my code sometime. Like, let me undo all these things. It's gonna be something like, if I take this create item operation and I do something like .result or .wait or get a waiter, get result, those are common bad practices that might cause thread starvation, thread exhaustion, or deadlock. So you might want to avoid those things when you are working with any async operation in your application with the SDK or with other async code that you might have in your solution. But these two things, these two ways in the diagnostics are things that we use to troubleshoot any issue that the customer might be encountering. And the other obvious is if you have a diagnostics on your environment, maybe you're running in an Azure VM or Azure App Service, you have CPU measurements there. So you can use those metrics to understand if you are in a high CPU scenario. The only comment there is you always want to measure the max CPU, not the average, because average always tends to hide the spikes. So if you have access to those metrics and you are experiencing timeouts more than what is normally expected, then check those metrics, check the CPU usage, the max CPU usage on the instances, and see if you are hitting these spikes or not. And that might be a cause of the timeouts. Now, if CPU is fine and we have no issues there, all the measurements are normal, the other possibility on the client side is connectivity timeouts. And this is something that you also mentioned earlier, Mark, about the SNAT port, the famous SNAT port exhaustion. So in the SDK, in the diagnostics, you will see this as transport exceptions. So it's transport exception is our way to say there was an error on the TCP connectivity, and these were the addresses or the ports that we tried to reach to. We couldn't connect, and this whole thing, it's a timeout because we couldn't connect, we failed, and this is the diagnosis that we have available. Now, what can you do from the client side to understand what was the reason for these timeouts when we are diagnosing client side or on the environment of the client? And the most common causes is the first one is the customer is not, or the user is not using the client as a singleton. Singleton means you have one instance and that instance is reused across the entire application lifetime. You are not creating multiple clients across the lifetime of the application. I've seen customers or users create a new client every time they want to perform an operation. The problem with this approach is every new client opens its own connections. So if you are creating multiple clients, each client keeps opening new connections and new connections and new connections. So imagine that a client's open 10 connections every time that you create it, and you keep creating, clients and clients and clients and clients and clients. At some point in time, you will reach the limit of amount of connections that you can open, and you're done. Basically, any new connection that wants to be open will time out. Depending on the environment that you run your coding, Azure VM, Azure App Service, Azure Functions, Kubernetes, or whatever is the environment, there might be a limit on the amount of connections, and the limit might vary depending on the machine size. Some machines are bigger than others, some machines have more connections available than others. So this error might hit not right away when you start the application. It might hit maybe a day after you have the application running or a couple of hours later. So the first thing that you need to double check is your application maintaining the client as a singleton? If it's not, then make sure that it does. The other point is, like I mentioned, different instances have different connection limits. Some Azure services have limits that others do not. And in those cases, there are some environments like Azure Functions on consumption mode. This slide has a typo. It's not consumption plane. It's actually consumption mode. The number of connections might be rather small. So in those cases, maybe it's better suited to use gateway mode. But this is after you rule out the fact that you are obviously on a singleton and you are within the connect, or you are exceeding the connection limit, and that is expected. In some Azure services like Azure VMs, if the IP of the machine is private, then this is enforced, and it's also called SNAT. But if you make your IP public, I think that limit is also lifted. Or if you have private IP, but you are using VPN or service endpoints, that limit is also lifted. But it really depends on the scenario. The first thing that you need to check is, do you have a singleton client? Yes. Are you in an environment that has limits? Which are those limits? Each environment might have metrics. Maybe you can access those metrics and see how many connections are you opening up. And also the SDK has a couple of configuration knobs that you can change on certain conditions. For example, If you expect your workload to be not constant, but rather spiky, like you are performing some operations during the day, you have a busy time, but then the operations kind of die down. Setting the Cosmos client options port reuse mode to private pool and the idle connection timeout on the Cosmos client options will make the SDK after the timeout that you specify in the idle connection timeout will make the SDK will start to close those unused connections. So it's kind of beneficial if you want to have a kind of control, a soft control on the amount of connections to kind of close the ones that you are not using.
What's the default for the connection timeout if you don't set that?
Forever. So basically, the SDK is meant to optimize the scenario where you want to have the lowest latency.
Yeah.
So unless you specify timeout, it keeps those TCP connections open forever.
Got it.
So with that, obviously, you don't pay the cost of opening a new TCP connection, but you have to maintain the connection open all the time. So depending on the scenario, you might want to set these connections to these different values. The amount of time, this is an example, you can adjust. I think the range is something between 20 minutes and days. And the reason you don't want to set it too low is because obviously you don't want to eagerly close connections that you might have otherwise reused in a short period of time.
Got it.
And again, I repeat this one because it's like
it's like a typo or not, but I figured no, because we see it so many times, right? So
yeah, it's the most common one. I've seen users use patterns like repository, where they are super sure that they are creating singletons for everything, but the client is not. And it's kind of like leaking the creation somewhere. So just be double sure, triple sure that you are maintaining a singleton client. The scenarios where you might want to have multiple clients is if for some reason your application is contacting multiple Cosmos DB accounts. Like you need to open two clients because each client needs a connection string, and the connection string is different for each account, right? And that is expected. But if you are just working with one client, with one account, then there isn't a reason for you to be creating multiple clients. Now that we covered the most common error cases on the client or how to troubleshoot them, there might be some cases when the actual problem is on the service, and it would be nice to kind of know which cases are what is expected and what actions you can take to on these particular situations. Now we saw that there could be high latency scenarios, and we saw that there could be potential problems on the client. There could be retries. There could be latency on the wire. Maybe we put the request on the wire. The request took longer to complete, and that's the reason for the high latency. Now, how do we tell apart the actual Cosmos DB backend from the actual latency on the wire? And that's something that we expose in the diagnostics. The diagnostics have this property called the BE latency in MS, right? It's kind of backend latency in milliseconds. And this basically shows what was the latency on the actual Cosmos DB backend. Now, if you see request, I think I still have these guys here. So this is one example diagnostics, right, where the backend latency was super fine. So we see backend latency less than 5 milliseconds, right? But the overall latency of the request might have been higher, right? Now the reason is the reason here is if I see the request taking longer, but I see the backend latency being very small, then I know the problem is somewhere in the middle. I know that the backend wasn't the issue, and I know there is a wire in the middle. So maybe it's a problem on the network. In Azure, there are support teams dedicated for network issues. So that could be one point of contact. But the other scenario could be maybe the backend it is actually having a latency problem. How do I diagnose that? Well, in the diagnostics, I will see, let's say that this operation took 305 milliseconds. And in the diagnostics, I see 300 milliseconds here in the backend latency. So now I know that this document read operation, for some reason, took 300 milliseconds, and the problem is the backend. Now I have evidence, and I can open a support ticket and understand what is going on my account. And these same metrics are also exposed in the Azure Monitor or the metrics in my account. I can actually track the server-side latency for different operation types during period of time. So I can build monitoring on top of my Cosmos DB account that is not particularly in my business application. So I can monitor these things both on the application and also on a monitoring layer. And I can act accordingly when I see this latency, going above what is expected. Now, this latency can also generate timeouts. I mean, I can have a high latency, which might not generate a timeout, but maybe when the latency or the backend latency goes beyond some threshold, that surfaces as a timeout. And that is, one of the cases for backend latency. Sorry, my English fails me sometimes. That is something.
Mine too. It's okay.
That is how backend latency can reflect in two different ways. Either you have requests succeeding with high latency, but you might have timeouts also on the same boat. So again, timeouts can happen on the client side because of client side issues like we have already seen, but timeouts can also happen due to something on the backend, and that could be also service side latency. Now, on the service side, the common error responses that we've seen are kind of mapping this table. And what I try to do in this table is which are the error codes, which is kind of the meaning, and if these are retried or expected to be retried, right?
Yeah.
On the application layer. So
I should point out, people should take a screenshot of this. I'll leave this up while you're talking to it, so people can take a screenshot so they can look at these meanings in here.
Yeah, and like you said, I mean, all these slides will be available on the repo for the live TV content. So you can just download them later and click on those URLs and check it out yourself. But the idea here is let's just go through the common ones and do a quick understanding. And if we, as a user, as an application builder, if we should add any type of logic to handle these situations. And the first one is a 400, which is bad request. Normally, there isn't any case where you should retry a 400. That means that something is wrong on the payload. It could be the payload you are sending is not JSON, or the payload you are sending has an invalid partition key, or is missing the ID, is missing the one of the required properties. So all this will translate into a bad request, and retrying won't really make any difference. A 401 means invalid authentication. So maybe it's the keys you're using are invalid. Maybe you are using the keys that you thought are correct, but someone rotated the keys on the account. So you are now getting a 401. Retrying a 401 normally is not, that won't change it. I mean, your keys are invalid and there isn't much to do about it. 403s mean that the operation has been blocked by access control, meaning you have some configuration in your account firewall or VPN that is filtering requests coming from a particular source. For example, you can create your Cosmos DB account and say, I only allow requests coming from this subset of IPs or these VPNs or these private endpoints. If a request comes from outside of these known sources, then they get a 403. Now, why did I put you could maybe retry these 403s? Is because when you change any of these polysizes, it might take something between 5 and 15 minutes to apply. So if your business scenario is meant to constantly or periodically change these configurations on the account, maybe you are periodically changing the allowed IPs or the VPN configuration, maybe you want to retry on a 403 because it might take a couple of minutes to reflect those new IP or those new enable IPs. Normally, you wouldn't, but maybe in your business applications, you decide to retry on a 403. 404 means the resource you're trying to read doesn't exist. There isn't a point in really retrying anything here. I mean, the resource really doesn't exist, so there isn't any more about it. 408 is a timeout. Like I said before, timeouts can happen in a normal scenario where everything is perfect. Timeouts can still happen. Now, the SDK already internally retries on timeouts for read operations. So when you are issuing a read, which is like a read document or a query, if the SDK faces a timeout on the connection, it will retry internally a couple of times. Now, if the timeout surfaces, it means the SDK retries were exhausted. You can, and it is advised, to actually have your own retry mechanism and retry on timeouts. Again, because timeouts can happen. And if you're building a resilient application, then you should keep retrying on timeouts. The only caveat or the only scenario where you might want to decide not to retry is for write operations. And the reason is, imagine that you're on the wire and you're doing a write operation. You put the request on the wire, and that request is traveling on the wire to the account. And we on the SDK get a timeout because we didn't get the response in the expected time. The problem is the SDK won't retry a timeout on a write, and the reason is we don't know if the payload that we just sent reached the backend or not. Maybe the request got a timeout in the middle of the wire, or maybe it reached the backend, but the problem was sending the response or receiving the response. So that's why the SDK doesn't retry on a write timeout. On your application, you might decide to do a retry on the write, but you should be advised that you can expect two possible outcomes. One is the write actually succeeds because the timeout was kind of in the middle. It never reached the backend. But the other possibility is that you get a 409 or a conflict. For example, because the document that you just created did actually hit the backend, but the timeout was on receiving the response. So when you retry the write hits the backend, and it sees, for example, that the document already exists.
Makes sense.
So
you're going to want to nest those status codes, basically.
Exactly. Like I said, I mean, you can retry on reads, no problem. You can retry on writes, but if you retry on writes, expect that there could be some 409s.
And it should go without saying that if you're writing apps in the cloud across a WAN, you need to have some sort of retry. Everybody should be using Poly in their application, making requests across a WAN. It's just, this is minimum stuff. You have to do this because the WANs are flaky. You just don't know what anything can happen between the time that code leaves your SDK and your compute instance to when it hits either our gateway or our backend. So
exactly. I mean, there could be, this is a distributed compute system, right? You are writing a distributed application, so you need to keep in mind and write code that is defensive against any potential failure in any of the components.
Yep.
The other code that we know is 412. 412 happens on what we call optimistic concurrency. Not everyone uses optimistic concurrency, but what this does is it lets you do a replace or an update of the document that enforces the fact that, let's say that you have, let me rephrase it. Let's say that you have an application that might be writing on the same or updating the same document from multiple places at the same time concurrently, right? And you want to enforce that any change that you do is kind of atomic, that you are not overstepping in the change or replacing the change that another part of your application or another application just did on the same document. So the optimistic concurrency pattern is you read the document, you capture the ETag property of the response, you apply your changes on that document, and you issue the update passing the ETag property. Now, if there were no other changes in that document between the time that you read, you applied your update logic, and you send the update, then that operation will succeed. But if there was some other concurrent operation that overwritten the same document, then you will get a failure with this particular 412 status code. What you should do is you should retry the operation by doing another read of the document to get the latest state. Again, capture the tag, apply the update logic, and then retry the update operation on the SDK. But that's why you should still retry on 412s.
Yep.
413s is basically you are exceeding the max document size. There isn't any retry in there. If I remember correctly, we have a 2 megabyte document limit. So if you are trying to store something really big, this will fail, and there is no retry that will save you.
Yeah, the only thing you can do is shred the document and then delete the original.
Right. 429s are throttling. The SDK already retries this internally up to a particular amount of time that you can change using the Cosmos client options. But normally we retry, and if you get a surface of a 429 error code or exception, it means that the SDK already exhausted all the retries internally and is throwing the error back to you. You can either increase the configuration to retry more times, or have your own, like you mentioned, Mark, you have poly, and you are deciding to keep retrying on 429s because you want the operation to succeed regardless. Ideally, what I would do is try to measure these 429s and see how many I am getting, because ideally I wouldn't like to have any. So in those cases where I'm getting too many, it's a time to again ponder: is my provision throughput enough for my workload? Should I reduce my workload, use autoscale, increase the throughput? Those are things that I should evaluate if I'm hitting too many 429s.
They're okay once in a while because at least you're saturating the throughput you've been provisioned. So it's not, you don't want to avoid them at all costs, but you're right. There is a tipping point where it's like, okay, something needs to be addressed, whether it's increasing throughput or I need to look at how I'm accessing my data and how I'm doing these operations.
Exactly.
Yeah.
The other error code is 449. 449 is retry after. It is not common, but happens when you have multiple write operations, mostly using store procedures, on the same resource concurrently. The SDK, again, retries internally on these guys, but you might want to also retry if you are building your own retrying layer. And it's safe to retry on those. We have two left. One is 500s. So 500s are kind of like a weird ones. Normally, this means that something is really wrong, and you don't really expect this. Now, some users have been asking me, should we retry on 500s? And the answer is maybe. So the problem with the 500 is, for the SDK, we have no clue what's wrong. I mean, we only know something is not right on the backend. Retrying might help. Maybe, I would say maybe one retry on a 500, because maybe this 500 is something temporary.
Yes.
And we are trying to build resilient applications. So with that in mind, having a one retry on a 500 or a very limited amount of retries on 500 might help. In the case that this 500 is something transient, that one bird just was hitting or eating the
500
wire.
is why you have things like poly, because God knows what that was, right? And I've seen that so many times. Like, what the heck was that? And then retried. Like it was never there. So
right, exactly. So maybe one or a very limited number of retries is actually just fine. And the 503 means service unavailable. So normally what this happens is we have a high number of TCP timeouts on the connectivity layer, and the SDK surfaces that as a 503. How to handle a 503? It's exactly the same as timeouts. So if you are building some logic to retry on timeouts, you can do the same thing as 503s, because 503s normally mean there was a high number of TCP timeouts. We just couldn't connect at all to the replicas. and you can safely retry. I mean, we retry internally, but you can safely retry. Now, again, going back to the things I said about timeouts, having a 1, 2, maybe a couple of these in a fixed amount of time might be expected. We are building a distributed application, but if you are seeing like 50% of your request, 20%, 10% of your request failing with timeouts or service unavailable, then something is wrong, and we need to start diagnosing that. And talking about availability, the last topic that I wanted to discuss is what happens on regional failures. We know what might be going wrong inside one region regarding connectivity, but when we start to span multiple regions, then how does the SDK behave in terms of failovers, or if a region goes totally offline, what happens? I mean, will the SDK try to save me or save my application by doing something? Okay, let's see what's up. So let's assume that I have an account with regions A, B, and C, and I have an SDK client that is set with a regional preference, like we've seen in the earlier slides, with region A, C, and B. Note that it doesn't map exactly the list of regions in the account in the same order. So I start my application connects to region A, it's performing writes and reads without issue, but something happened, or not something happened, but I go to the Azure portal and I remove the region. Or let's hope not, but the region goes completely offline. Now, this region going offline can surface on the client in 2 different ways, depending on the SDK, if the SDK is actually doing operations while the region is going offline, or the SDK is trying to perform an operation while the region is already down and it's not reachable. Now, if I'm performing an operation and region is offlining, or I'm, the process of removing the region, because I went to the Azure portal and I click, I remove the region and I click the save button. So the region is starting to the offlining process. The SDK gets one particular response from the backend, which has a status code of 403, sub-status code of 1008, that tells the SDK, this region that you are trying to contact is offlining, is no longer available, or is becoming not available. The other possibility is if the SDK is trying to perform an operation on a region that went offline and is completely down or removed after some time, we won't be able to resolve the DNS. So the regional DNS for that particular regional account is not available. So in any of those cases, what does the SDK do? Is it contacts again Gateway. It tells Gateway, hey, Gateway, which is the account information? Now, tell me which is the topology, which are the available regions. So if I just remove the region A on the portal, that will return to me region B and C. If the region A is still part of my account, but there is a regional failure, that region will be marked as unavailable on the SDK, so the SDK won't see it anyway. So for the SDK, it's going to be region B and C. So since I have a regional preference of using region C or as the next region when region A is not available, then the SDK will connect to region C and retry that particular operation and all subsequent operations from that point in time forward. So there isn't anything that I should do on the SDK itself. The SDK will take care of detecting the failure and reacting accordingly when provided with the correct configuration and information. Now, there could be, maybe, hopefully, a time when that region A goes back online, because we are going to region C, but maybe that's due to latency. That's not the ideal. I mean, these are still 2 different Azure regions, so maybe operating on region C is having a bit more latency than operating in region A, and that while that gives us availability because our operations are now succeeding, it's not great from the latency perspective. So what the SDK does is every 5 minutes, it keeps asking Gateway to know which is the state of the account, which is the topology of the account, to understand that maybe region A, maybe region A is now available again. So what happens is once the SDK detects after a gateway interaction that the region A is now back up online, it will, sorry, I forgot to grab some water.
You got water. Here, we could give you some of mine right here.
So once it detects that region A is back online, because region A is higher on the list than region C on the preference, then it will switch all the traffic from that point onward to region A again. So in a scenario where there is a regional failure and region A went offline, and we went to region C to keep providing availability, there is a case where without the user interaction, when region A comes back up, or if I went to the Azure portal and I re-added region A, the SDK will reroute all traffic again to region A based on the regional preference that I set on the client creation. That's why it is super important that either through the application region or the application preferred regions, you are setting and describing which is this regional preference for your account to the SDK. Otherwise, the SDK won't really know if you rather stay on region C or you prefer going back to region A. Now, there could be another scenario which is particular to single master accounts or single write region accounts. Only have one of the regions which acts as write region. The others are read replicas, right? So let's assume that, again, I have ABC and A is my single write region. So all my writes go to region A on my client. And because I'm setting the preference to region A, all my reads also go to region A. Now I go to the Azure portal, and for whatever reason, I do a failover of the write endpoint or the write account or the write region. I say, okay, I don't want region A to be my write region anymore. I want it to be region B. Now what happens is once that process completes, the backend, when the SDK tries to perform a write on region A, the backend will return an error saying HTTP 403 substatus 3, which the SDK will understand as this region that you are contacting, while it is a valid region, it cannot serve write request. So what the SDK will do is it will, again, contact the gateway, discover which is the new write endpoint, and redirect that write request to the new write endpoint. Note that region B, in this case, it's not the second one of my preference list, but because this single write region account doesn't have any other write region, there isn't any other alternative. So my writes will start from that point onward to go to region B, but my reads can still honor the regional preference. They can still be served from region A because region A is still a read region. Now, another scenario is session consistency. So we know that Cosmos DB has 5 different consistency levels. Each one has its pros and cons, and users should be picking the consistency that maps their business requirements. One of them is called session consistency, and the tenet of session consistency is you should always be able to read your own writes, right? So what happens in this scenario? I have my writes going to region B and my reads going to region A. Now what happens on the back end is when I do a write on region B, that write gets replicated to region A. Now one more slide. So let's say I do an operation on region B. That operation has a transactional identifier of two. I'm not saying that two is what we use to identify transactions, but it simplifies the scenario. So let's assume that I write a document, that document has transaction number 2, and the backend in region B returns to the client, hey, your session, what we call the session token, which identifies which is the latest transaction that you just did, has a numeric transaction of 2. So the SDK says, okay, my session is now 2. And when it tries to read the document from region A, it will tell A, hey, I want to read the document, but I want to read it in the scope of session 2. The problem is region A might not have yet received the replication of that operation from region B because, I mean, we cannot beat the speed of light yet. So maybe my read is faster than the speed at which the replication is happening. So in that case, region A will tell the SDK, hey, this document doesn't exist in this region yet. This is a 404 with a particular substatus code that is 1002. When the SDK receives this particular error code, what it does is it goes and retries that read operation with on region B, because it knows for certain that even though that might not be your preferred region, but it knows that that document exists in region B. So it retries the request in region B and then serves the result. If there is any subsequent request, those requests or read requests, those requests will still go to region A. But this particular request that had this particular error code gets retried on region B. And if we go to the diagnostics, we can see the requests going to the different regions with the different error codes that were involved. So the point here is, if we had a high latency request and we want to investigate why this request had high latency, this is one of the potential scenarios. We could be hitting a replication delay in between the regions, and the SDK is just retrying on the other region, getting the results for you to have availability on your application.
I get a question for you. So the SDK is what handles consistency for bounded staleness and strong, right? So doing the 2 replica reads, is that correct? So
correct.
It's checking the LSNs to make sure that they match. That's how we guarantee strong consistency, or at least in region strong for bounded staleness.
Yep.
But let's leave that aside. Let's just say it's strong. Well, no, I guess let's talk about bounded staleness, because strong consistency is global quorum. There's a different mechanism that's going to force that replication. So that's not client-side driven. That's back-end driven.
Correct. But bounded staleness is a good scenario. I mean, in bounded staleness.
So let's walk through that scenario again. So I write into region B, and I'm using bounded staleness. So I'm going to do a 2 replica read off of region A, and I'm likely to get mismatched on both replicas, or on one of them at least. Or let's just say it's both. None of the data is replicated. So am I going to get that same? Am I going to get that same code?
No, this error code is particular to session consistency, and the reason is, on bounded staleness, when you set bounded staleness on the account, you are acknowledging that your reads can lag in some particular lambda or some particular delta. So
makes sense, because it only applies to it only provides in region strong.
Exactly.
And we're not doing in region reads; we're doing out of region reads. So
So in that case, if you're using bounded staleness, hopefully you are building an application that, when it's performing the reads, knows that it can get a 404, like a plain 404, from the other region, and that might be expected. In that case, maybe you want to retry those 404s, because that's within the bounded staleness configuration that you are setting. Now, when you're using session consistency, that is the part where the SDK kind of takes over, because the session consistency is telling, or has that tenant that if I'm using the same SDK client, I should be able to read my own writes, regardless of where I'm reading, right? So that's when the different error code appears, and that's when the retry mechanism on the SDK kicks in in order to honor the session consistency.
Makes sense. I mean, that's the difference fundamentally from session consistency amongst all others. Is all the other consistency models are all data driven, and session is unique in that it's a client driven consistency model. Thus, the session token that you're passing around between requests. So, that makes sense.
And in the cases where you have maybe different components in your application, where each component has a different client instance, what you want to do is you want to pass the session token. The session token is part of the response of your operations. So if you want, for example, one component to write the document, and you want another component to read the document, but that other component will potentially have a different client instance, you want to pass the session token from one to the other. So the second one will perform the read, but pass the session token from the write, from the client instance that did the write. That's how you extend the session scope outside your client instance.
Are you saying basically making the session token durable outside the instance?
Exactly. I mean,
I've,
there are two. Yeah, go ahead.
I just was going to say I've talked to customers and others about doing that. I think the only thing that could cause issues is in high concurrency situations, you could end up with contention on the single resource, which can add latency because the clients are going to be retrying as they try to do sets or reads on the session token within there. So you could basically be working against yourself, and that if you have a high concurrency scenario, you may be introducing latency if you try to do that.
Yeah. The thing is, either you do that, or you know that a different client instance has a different session scope.
Yeah.
And outside of on a different session scope, then you can expect the normal 404 because that other client has no recollection that there was a write originally, and has no information on what was the transaction identifier of that write. So this is a kind of like a blind read, let's call it like that. And a blind read is, okay, does the document exist or doesn't? Yeah. And if I'm reading on region A without the session token, in this case, I will get a 404, like a plain 404, and there is no retry on the SDK.
Yeah.
And finally, the one is the 503s, which is temporary connectivity problems. Like you mentioned before, 503s mean TCP connectivity issues, too many timeouts, cannot connect. So we surface a 503. Now, what happens is on that particular operation, let's say I did the write on operation 1, I try to do the read fails with a 503. What the SDK will do is just for this particular read operation, it will retry that read operation in order to provide more availability. It will retry that read operation in the second preferred region. So if my preference is region A and C, it will go to C and retry the read and hopefully succeed, because hopefully this was just a hiccup in the wire to region A. If this succeeds, the next read that will happen will just keep going to A. So the SDK retrying on 503s is what we call a request scope retry, meaning this request will only get retried and not the other request unless the other requests are also hitting 503s. So this is another reason for you to actually populate your regional preference, because otherwise this particular retry cannot be done on the SDK. If you are not populating the regional preference, we cannot retry on a 503. You get the 503 and you decide what to do, if you want to retry yourself or not. But if we know your regional preference, we can do one retry to know if we can save the operation and provide with availability on the SDK itself.
You don't have a preference, do you? I mean, you can set application region, in which case we'll read in kind of the array of next closest regions and fail over appropriately, or you can say, no, I want you to read over. I want you to fail over in this order. You should at least choose one of them, right?
Exactly.
Okay.
Going back to, I think here was a slide.
I think what you're saying is don't not do that. Do at least one.
Yeah, pick whichever is best for your scenario, but do one of those, please. Yeah. I mean, mainly for your own sake as application and developer, because we will, if we have that information on the SDK, we will try to provide you with the best availability possible, honoring those configurations. If we are kind of blind, it makes the whole thing much difficult to help you with.
Makes sense.
So, in conclusion, the things that I wanted you to take away from all this presentation is, please always please use the client as singleton. Make sure that you are not creating multiple clients if you want to avoid connectivity issues, SNAT or connection exhaustion. Define your regional preference when initializing the client, which is the things that we were just saying like 1 minute ago. Please use application region or application preferred locations to hint the SDK which regions you want to connect to. Again, there could always be timeouts. you need to define some sort of retry layer on your application for some of the scenarios that we already talked through, particularly on timeouts, because this is a distributed compute system. Things can go wrong in any component in the middle. Capture diagnostics on errors and or on high latency scenarios. So if you are measuring the latency on your operations with your own stopwatch or by using the elapsed time on the diagnostics, capture those diagnostics for the operations that are going over some limit. You can use that information to troubleshoot that, or when you're in a support incident, we can use that information to troubleshoot it for you. And on errors, I don't see a reason why you wouldn't capture the diagnostics. And regarding the regional failover, which is a very common question, I mean, what happens on my application when a region goes down? Then review the documentation that we have available. It's basically, it goes over all the scenarios that I mentioned on the slides. If you have any questions on that area, ask us, and we'll make sure to improve the documentation with any feedback that we receive.
I wrote a bunch of that stuff and rewrote it. It's hard trying to explain that stuff in a way that's clear for people. I mean, you want to be as concise and as clear as possible on what the system behavior is when a distributed database is going through a failover, right? So how your application is going to behave, right? So I mean, that's why they're using Cosmos, is we can survive that kind of thing. So
exactly, and it's all live documentation. As the service improves and the libraries evolve, we can improve that information, or there might be some scenarios that we are not clear about, or maybe we are missing on the documentation. And you as a customer, you bring the question, we answer it, and we say, oh, I mean, I'm sure this can help someone else. So we add that to the documentation.
Absolutely, that's we're always trying to improve our docs and make things more clear with that. So just a couple of comments or questions here. Just someone saying thank you for such a detailed session there. I agree. This has been quite a session there. Someone else, you guys planning on update our examples on GitHub? I guess that's all the SDK samples that we've got there. Yeah, those have kind of been sitting around for a little while. I guess maybe we could, I don't know.
I mean, we were discussing earlier, in fact, in our SDK Scrum, we were actually discussing about adding some samples regarding these retry logics that applications could use, maybe using Poly, to have something as I mean, if I'm starting from scratch, I mean, do you have anything that I can use as a boilerplate? I mean, if I use this sample code that you are providing me, it covers the most common retry scenarios, and I can add on top of that. So that's one of the things that we are discussing. And obviously, adding more documentation that explains which are all the different scenarios and when you should retry and when it doesn't make sense.
I think there's a lot of good docs on Poly and stuff that we could maybe just kind of just suck into our stuff and create like a, here's some stuff, you need to kind of do before you go into production, right? And one would be implement retry, maybe implement some sort of logging with the diagnostics. I don't know. The hard part is it's kind of a slippery slope. Like I'm going to capture diagnostics, and then I need to somehow persist those somewhere. You're kind of out of the. Now you're kind of out of the thing. So, another question here. Any ETA for 4.0?
For what? Sorry.
.NET SDK 4.0.
So 4.0 before it's kind of like it's still in experimental phase. The only reason that you might wanna attempt to use before is because you want to use system text JSON. One thing that users often don't know is that you can use system text JSON with V3 SDK. So I actually have an Azure Friday recording with that. I don't know if you can we share some links like right now?
You want me to see if I can find it? Hold on.
If not, I mean, I can just add it to the folder in the repo, kind of like other links, or maybe add a slide to this presentation and update it on the repo.
Bulk and transactional batch operations. That's not it.
No, but it's Anyway,
Yeah.
there is no ETA on V4 right now because we are focusing on hardening and improving V3 to be the most solid base when we do go to V4. So if your question is, do we have a date? No, we don't. Now, I would ask you, which are the reasons that you are looking at V4? If you're looking at V4 for system.json, we can leverage system.json on V3. I will make sure to post some stuff on Twitter. So if my handle is at EALSUR, so just ping me there, and I'll make sure to send the
Yeah, and I'll see
pointers.
it and retweet it as well. You can just, if you hashtag
Yeah.
it with the Azure Cosmos DB hashtag, I will see it and retweet it. But yeah,
Awesome.
you can watch that and then figure out how you can use system.json with
Yeah.
that theme software, which is we ship with. So
yeah, the other case for V4 is maybe you want to use async enumerable in .NET. That is something that we are also looking for adding on V3. So the transition from V3 to V4 is going to be much simpler. So that will be something that you will also have on V3. So I don't see any other scenarios where you might want to use V4 right now. It's still there, but it's experimental, not currently recommended for production usage.
yep, definitely not ready yet. So great. Well, let's see. I want to.
We are working on it.
See,
it doesn't mean.
Yeah, right. That's right. If people are interested in seeing Matias's deck from today's presentation, which has all of those pretty awesome URIs, those AKMS URIs for all the HTTP responses, you can go to this URL here. Just look for the folder with episode 13, Advanced.NET SDK, and you can get those within there. I think I've got one more question, maybe. No, just Will saying, sweet, cheers. So, good. Well, fantastic. This was quite an amazing episode this week, Matias. Thank you so much for joining us. This is great. Thank you very much.
Thank you for the opportunity. For me, it's a pleasure.
Yeah, it's great. Well, everyone, thanks for joining us this week. Next week, we're going to talk about our new continuous backup and point-in-time restore feature. I think we announced this, at Ignite, Winter Ignite, so that would have been like back in February. So come and check out. You're going to join a teammate of ours, Govind, and he's going to talk all about this new feature. So for myself and Matias here, thank you very much for joining, and we'll see you next time. Bye-bye.
Bye-bye.